Uh, okay, guys, we're back here. This problem. So it says calculate. This is continuation for the previous lecture. We want to calculate the work done by all forces acting on the box, and we mentioned that how many forces are acting on the box. We have the 100 Newton, the friction force, the normal force, and the gravitational force. We should not forget that. So how many forces are acting? Four forces. So when we say we want the work done by all forces, literally we are looking for four different work due to four different forces. But luckily, we don't have really to go through all of them, because if you recall, what was the work formula? Let me use my pen. Oops. What was the work formula? It was F dot product with D, which is F D cosine theta, and theta is between F and D. What is D? D is the distance the object travel, which is 20. For all of them, distance is 20, for all of them. Now, immediately, because I told you that most of the exam will be multiple choice, you can cancel out the forces which will not produce any work. Some forces will produce work, some will not produce work. Which forces will not produce work? Now all of them have values, right? All of them, they will have also D. So it is the theta between F and D which will lead us to having work from that force or not. So let's see. This is F is equal 100 Newton, and D is anywhere in this direction, right? So what is the angle between 100 and the D? It is 0. So cosine is 0 is 1. All right, so this is not a 0. What about Fk? What is the angle between the D and the Fk? Always we mention that it is 180. What is cosine of 180? Minus 1. So it's not a 0. So work will be produced due to friction. Now, what about the normal force? What is the angle between the normal force and the displacement? It's 90, right? It's 90. All right, cosine 90 is 0. So there will be no work done by the normal force on the object. Okay, the fourth force, Fg. What is the angle between the D and Fg? This is the D and this is Fg. The angle is 270. What is the cosine of 270? It is 0. Of course, even if you don't go through this much, you say, this is perpendicular to the distance. This is perpendicular to the distance. Since it's perpendicular, so the work done is 0. Move on. So we want the work due to 100. We want the work done due to the friction force. All right? Because this is a multiple choice, so you really don't have to go through all the work, unless otherwise you are asked to show the work. All right? So the net work performed by the box, we say that these are the four forces, and if N and mg, both of them are perpendicular to the distance, so they will produce work of 0. But the work due to the 100 Newton is, again, this is the 100 Newton, and the object is anywhere moving in this direction. So the angle is 0. So this is the work in joule, and then also the work due to the friction is this is the D, this is the friction, the angle between them is 180, and this is negative, so the work due to the friction is negative. So what is the net work on the object? It is this work plus this work. All right, guys? So I am done with this example. So the work net is due to two forces, the applied force and the friction force. Now the question could be a simple multiple choice question, a very nice written question like this one, but it will say, find the work done by the gravitational force. What is the answer? 0. Find the work done by the normal force. What is the answer? 0. You don't have to go through any of these things. You just quickly sketch the free body diagram to make sure that they are perpendicular to this displacement, and you can tell that it is 0. It could be what is the work done by only friction force. All right, guys, you have to read the question so that you will use your time wisely in the final exam. Final exam is not very difficult, but it's about how you will tackle the questions and how wisely you will use your time fast. And you have a lot of multiple choice questions, so you can practice on these things. So I am done with these notes. All right, let me now just go through some solved problems. Let me see, is it this one? No, this is done anywhere. Just a second, guys. No, don't save. You will get it anywhere. And here, solved examples. Oh God, I should have opened it before you guys were here. 1 minute. All right. Anyway, before that, let me, since the Word document open already, let me just write some kind of things to you guys. Okay, here in brief for chapter 6. Chapter 6, if I will really write the formulas for chapter 6, I would start with work energy principle. And this is work energy principle. What is work energy principle? Actually, in physics 2, this is what I start with always, because we finish in chapter 6 and then we start something related with chapter 6 in STEM 2. Work energy principle, it's relation between work and energy, but which work? It's the network. Which energy is the kinetic energy? Which kinetic energy? The difference in the kinetic energy. So we have actually 3 main points. It's not only the work, it's the net. It's not any energy, it's the kinetic energy, and it is the difference or the change in the kinetic energy. So this is called the work energy principle. What is the work net? It is the work due to all kind of forces on the object. The conservative forces plus the non-conservative. Again, we have conservative forces and we have non-conservative forces. The conservative forces will lead or will produce conservative work. The non-conservative will produce non-conservative work. What is the most famous example about the conservative force? Is the gravitational force. What is the most famous example about the non-conservative? Is the friction force. All right? So this is due to all of them is equal to the change in the kinetic energy. Very good. Now, since one of the most famous example of the conservative force is due to gravity, if you recall the very famous example that this is the ground and this is a bottle of water or stone, and we move it all the way to a table here, and while moving it there, up there, okay, we are conserving some kind of energy here, and then here at this point the object will have potential energy, which is mgh. Now, what is the direction of the gravitational force? We all know that this is the direction of the gravitational force, and this is the direction of d. So if we say what is the work due to the gravity, which is of course the work of the conservative force, it will be Fg times d times cosine of the angle between F and D. What is the angle between them? This is a D, this is F. What is the angle between them? It's 180. All right? So this is minus Fg D. All right. What is Fg? It is minus mg times d, which if you see, it is the negative of the potential energy difference. If this is the potential energy is 0, so delta PE is mgh, right? So what is the work due to the conservative force, which is the work due to the gravity, is minus delta PE, all right? Because delta PE is mgh, okay? And this is minus mgd, which is the h basically, so it's minus because we are going against the gravity. I hope that this is clear. We are going against the gravity, and that's why it's minus. Okay, it's 180 degrees. And the delta BE is mgh, all right? So it is minus delta BE. So let me write here the WC, which is the change in the potential energy, the gravitational potential energy, plus work of the non-conservative forces is equal to delta KE. Let me say for conservative system, okay, we will assume that no friction, okay, so the work due to the non-conservative would equal to 0. That makes sense. This is conservative system. When we ignore the friction on the surface, we ignore the friction in the surface. So this is 0. Can we rewrite this equation? Yes. Bring this one here. Okay. So 0 is equal delta KE plus delta BE, which is kinetic energy final minus kinetic energy initial plus potential energy final minus, where's my pen? Okay, minus potential energy initial. Can you rearrange this? Keep the positives here, kinetic energy final plus potential energy final, and bring the negative to the other side. This is mathematics. Kinetic energy initial plus potential energy initial. Do you remember what is this? That we've been solving problems about it? This is the conservation of energy principle. Principle. That the energy will not be lost, neither created, but it will transfer from one shape to the other. But here, you remember when we say mechanical energy at any point is equal to mechanical energy at another point. And this is the conservation of energy principle, all right? So from work energy principle, we could derive the conservation of energy principle for conservative system. This is very important, guys. You can go through this slide again and again because it will really give you full understanding for chapter 6, okay, about the work energy principle and the conservation of energy. All right, guys, I will see you in another YouTube for more examples.